Hello, everybody. We are on lesson 2 of chapter 6, equilibrium, and here we will discuss about condition of equilibrium and center of gravity. Uh, in lesson 1, we had covered the following topics. We start off with talk, that turning effect of a body, and equilibrium, the kinds of equilibrium that you have, uh, static and dynamic equilibrium. Static equilibrium when the body is at rest and the forces acting on it is zero, and dynamic equilibrium when it is in motion, constant velocity, the acceleration is zero. And then we moved on to states of equilibrium where we discussed about stable equilibrium, unstable equilibrium, and neutral equilibrium. So to, um, in this lesson, I will be discussing about conditions of equilibrium. Now, remember there are two conditions for a body to be in equilibrium. Um, I'll explain the first condition and then the second condition. Uh, First condition of equilibrium is that when body is said to satisfy the first condition, the resultant of all forces acting on it is zero. Now you can see over here an example is given that the force is acting on this body, and this body is at rest, and all the forces acting on this body, whether the reaction force, the weight acting downward, leftward, whatever forces, the total number of forces that is acting on it, F1 plus F2 plus F3, so on and so forth, n number of forces acting on it, the summation of all this is equal to zero. So when the summation is denoted by Greek letter sigma, and we have the first equation, that summation of all forces F acting on it is zero. Now, if the force is acting horizontally and vertically, let's say along x-axis, so the x component of forces will be F1x plus F2x plus F3x plus so on and so forth up to Fnx, okay? And the summation of all forces acting along x-axis, Fx is equal to 0. Similarly, the forces along y-axis, F1y, F2y, F3y, F4y, so on and so forth up to Fny is equal to 0. So all this can be written down as summation Fy equal to 0. That means sum of all forces acting along y component is equal to 0. And we already know that sum of all component acting along x-axis is also equal to 0. Now, examples of first condition of equilibrium are as follows: a book lying on a table, a picture hanging on a wall at rest, and thus it satisfies the first condition of equilibrium. A paratrooper coming down with terminal velocity. Now, when you jump off, you see this paratrooper coming through the parachute. There are two forces acting vertically, one downward and one upward. Okay, the upthrust you could see, and the weight which is acting downward, and it satisfies the first condition of equilibrium because the force is acting along y-axis, so you could say it is an equilibrium. Now, second condition of equilibrium is when it satisfies when the resultant torque acting on it is zero. Now, torque, is turning effect of a body force into displacement. Mathematically, we say that tau is equal to zero. We discussed it in the first lesson. So here you can see an example of two children sitting on a seesaw. On the left hand side, we can say the weight acting downward, W1, the mass of the child is L1, and the distance between the weight and the fulcrum, FP, is R1. So the torque would be the force acting and the distance. In the same way, the curl on the right hand side, as you can see, the weight acting downward, W2, mass of the child is M2, and the distance you could see is R2, the fulcrum to where she's sitting, where the weight is acting upon. So it is balanced at this position, so the turning effect would be zero, tau is equal to. Second condition of equilibrium, you have examples like just explain it to you. Children playing on the seesaw and the force applying on the steering of the car. These are the two conditions. Okay. Okay. Now let's move on to the center of gravity. Now, center of gravity is a point where the whole weight of the body appears to act vertically downward is called center of gravity of a body. Now, a body is made up of large number of particles, and as you know that the gravity is a pull, which is in the downward direction. So the pull of the earth acting on a particle is equal to its weight, W. W is equal to mg. You know that. These forces acting on a particle are of a body are almost parallel forces and single equal to the weight of the body. So we say a point where this resultant force acts vertically towards the center of the earth is called the center of gravity. Okay, as represented by capital G over here. It's basically it consists of a small metal bob made up of brass or lead supported by a string. You must have noticed the painters and the masons using it uh, when they take a certain level. So here we use a plumb line and we marked three points A, B and C on this card which is of an irregular shape, and we first allow the plumb line to pass through point A, you can see over here, and mark the outline. In the same way we then hold it towards point B upright and allow the plumb line to pass, and we do the same for point C as well. So the intersection of all three lines will be common and the position where uh, the G or the center of gravity acts on. So they have a common point G, and this common point is the center of gravity of the car. So I hope it is clear to you all about center of gravity and the conditions of equilibrium. Remember, we did do two conditions of equilibrium. The first one is was uh, when you have body forces acting along x-axis and y-axis is equal to 0. So and this along horizontally or vertically should be 0. And the second condition is that the torque, the turning effect of the body is equal to 0. Like we did do the I did show the example of the two children sitting on the seesaw and how they were balanced at a certain point. So we also discussed about the center of gravity, how to calculate the center of gravity of an irregular shaped body with the experiment of the card and the plumb line. So I hope it is clear to you all, and hope to see you in the next lesson. Till then, take care.